Welcome back! In this lecture, we're going to showcase the difference between arrays and lists in Python and explain why there is a need for both. For starters, let's define a list with the numbers from 1 to 6. We start by creating a variable. Let's call it list A and set it equal to square brackets. Then, within the brackets, we write the numbers 1 through 6, separated by commas. If we call the len function, we'll see that its length is 6. This means that it contains 6 elements. Just like arrays, we can split lists into smaller increments by adding another set of squared brackets, both on the outside and the inside. The inside ones separate the data into smaller lists, while the outside ones indicate that these small lists compose a single variable. If we call the length function again, we see a different output. Instead of 6, this new version of the list contains 2 elements. Hence, Python sees this as a list of lists. This syntax might look familiar because it's similar to how we define ND arrays. The only difference is we also use the npArray function to create ND arrays. Therefore, we can just plug in lists as the inputs of the npArray function. So let's quickly create an ND array called array A by passing the list A as the input argument. Great! Before we move on, let's check the types of the 2 variables we just created. Unsurprisingly, list A is a list and array A is an array. So, even though the syntax resembles arrays, Python recognizes lists as a separate data type. We saw the 2 variables have different types, but what do they look like? Let's use the print function and compare how Python displays arrays and lists. Lists showcase all the values in a single line, while arrays stack them like a table with 2 rows and 3 columns. This is interesting because even though these variables contain the same data, their outputs vary. That said, you'd probably guess that Python must be storing them in different ways. Let's check if that's the case by comparing their shapes. If we reference the shape attribute of the array, we see a tuple with the values 2 and 3. Therefore, the array has 2 rows, each of which has 3 columns. If we do the same for the list variable, we get an error message. That is because by construction, unlike arrays, lists don't have shapes. This also explains why all the values were displayed on the same line earlier. See? As opposed to that, lists have length. We can find it using the length function, len. As we already saw, if we call this function on list A, we'll get 2 as the output. This seemed odd at first because we have 6 elements in the list, right? Well, this length indicates how many smaller lists are a part of the bigger list. Or, if you want to use better terms, how many sublists or inner lists are contained in the nested list called list A. Next, if we want to determine the number of individual elements in each of the 2 smaller lists, we need to add bracket 0 bracket after list A. That way, we're indicating we're only interested in the first sublist, the one containing the values 1, 2, and 3. The outcome is now 3, which means there are 3 elements within this list, just as we expected. Naturally, we'll obtain the same output for the second inner list. We can prove this by executing the len function with an argument list A while indexing the value of 1 within brackets. Fantastic! So, the biggest difference between arrays and lists is that array operations work element-wise, while list operations don't. To showcase what we mean, let's create 2 new variables. The first one, list B, will be the sum of the 2 sublists in list A. Similarly, the second one, array B, will be the sum of the 2 rows in array A. Let's just print the 2 variables and discuss how they differ. We see that list B has concatenated the 2 sublists together. For anybody unaware, to concatenate means that the end of the first one has been merged with the beginning of the second one. In contrast, array B has summed up the first element of the first row with the first element of the second row. It has done so for each column. It is exactly the element-wise functionality we mentioned earlier. When it comes to operations like addition, multiplication, and more, arrays act in the most intuitive way. They compute the element of one array to its corresponding element in a different array. Because of this element-wise functionality, ND arrays have the added benefit of using built-in functions and methods. For example, if we want to find the squared root of the values of an array, we don't have to go through the entire process of importing the math package and plugging in the values of the array one at a time like we would with a list. As a matter of fact, if we plug in the values of a list one at a time, we still get an error message. While, if we plug in a single value from the array, we will obtain the square root of this value only. So, to showcase element-wise operations here, we can call NumPy's squared root function np.sqrt and plug in the entire array. For this example, let's go with array A. The output shows the squared root of each value within the array. Hence, element-wise functionality is a great advantage arrays have over lists when it comes to computations. All right. Now that we understand the distinction between lists and arrays, it's time to learn how different data types would store the same information. That's why, in the next lecture, we'll discuss how strings, objects, and numbers store imported values. Thanks for watching.